crossed off. Okay, and let's get a, let's see, before I do that, let me get this PowerPoint open.
And so once we finish chapter 2, we'll probably have to test.
Yeah, definitely.
And that'll cover pretty much everything in chapter 2.
Everything that we cover in 2 and that little bit we did in 1. Yeah. Okay. All right. So the slideshow is set up. I can go back and forth on current slide. Okay. Well, we got a black screen. This takes an inordinately long amount of time to do so, to open. And now I've got to hide presenter view and go through my function. Oops, wrong one. Function F10, function F10, function F10. All right. And now we have compressed scale for some reason. And anyway, here we go. Okay. You said we were finished with solution curves. We were talking about solution curves, and we got the first 2 bullets covered on page 39, moving to the next 2 on page 40. Remember the dy dx, okay, is a function of y, which in itself is a function of x, but dy dx isn't necessarily directly a function of x. It's a function of y alone, but y, remember, is a function of x. And that's either positive or negative in a subregion, I, because we identify those subregions by finding where it's equal to 0 first. That's the only places there is 0. So the horizontal asymptotes there, those y values. And then everywhere else it's either increasing or decreasing. It's monotonically increasing or decreasing. It can't be turning back on itself. Otherwise, you'd have either an infinite derivative or a 0 derivative. You know, it can't be either of those. Now, if y of x is bounded above by a critical point, C1, okay, then the graph of y of x must approach the graph, in other words, y of x equals c, every one of your c's is going to be a vertical asymptote. Okay, and they'll be approaching that one way or another, different ways, however. Okay. So if it's bounded above by a critical point, it's going to approach that. Below by a critical point, it will approach that. Now, what happens beyond your critical points? It could be going to infinity. Probably is going to infinity because it's monotonic. So it's got to be going. But it doesn't have to be doing asymptotically, either vertically or horizontally. It could just be heading up to infinity and beyond. Okay, that's something else. Okay, now, so let's go back. Example 4 is going to go back to example 3 that we looked at before. Same problem, but since it's a new day, all right. That was dp dt. Okay. Now, because t is your independent variable, we understand that p depends on t somehow. Okay. But the derivative doesn't depend on t. It just depends on p. That's what makes it a autonomous differential equation. It depends only on the dependent variable. Okay. Now, first thing we did to this was set it equal to 0, finding the horizontal asymptotes. Basically, they turn out being is the places where your derivative is 0. okay? And we found those exist at p equals 0. And of course the other one, you set that equals 0 and then solve for it, and you get p is equal to a over b. Okay. Now, they started out telling us that both a and b were positive quantities. A, b, positive. Okay? They are positive, both of them. So therefore, a over b has to be positive. Okay? So that split our range of the function from p, this is the p-axis, this is the t-axis. The range of the function, p equals 0 to p equal a over b. Okay? In these two places, your horizontal asymptotes are your slope of the function is approaching 0. Okay? Everywhere else, it's not. Okay? And they are functions, so therefore, they either got to be increasing, decreasing, or whatever. Okay? So let's pick some value in between 0 and a over b. And I suggested a over 2b. Okay? Or not. So that would be somewhere here. One half of a over b. Okay? So, and let's just see what the derivative is there. Well, I think we did this before, didn't we? That would be a over 2b times a minus b times a over 2b. Okay? Well, this b divides that b out. Okay? And you get, oh, I was going to say, where did that minus sign come from? That's not a minus sign, that was part of the horizontal asymptote. This thing right there. Should have put that in baby blue or something yet. So this would be a over 2b times a minus a over 2, which would be a over 2b, which again is a positive number, right, times a over 2, which is a positive. Why did it do that? No reason. Okay. And both of these are positive numbers, so we know your derivative is positive in between there. So this is an increasing function. Okay? Increasing between there. Okay? What's that? Do I do what? You don't need, all I needed was to know what the sign was. Yeah. This just picked a point in between there. Now, whatever is going on here is increasing. Out here, for negative t's, it has to be approaching 0 horizontal asymptote, and somewhere up here, it's got to be approaching 0 horizontal asymptote. It doesn't have to cross any particular place. You assume it probably does, but it doesn't have to. It just has to be an increasing function in between those. So let's do something that's above this, okay? For instance, 2a over b. Why not? Okay? And let's see what's happening there. And this again is talking about the derivative, not the function itself. dp dt is equal to, and second?
I was just thinking, why didn't you do just a, but then b could be like 1/2, and you can make a smaller by not.
Yeah, okay. Yeah, you could do that too. You could make b 2, but you get the same number, 2a over b, right? Right. Yeah, whatever. But if we assume p is equal to 2a over b, this would be 2a over b times a minus 2a over b, b times 2a over b, sorry about that, I forgot the b, okay, and the b's go out again, they're dating, okay, and this would be 2a over b, which is a positive number, because a and b are both positive, and this will be negative a. A is a positive number, so this has to be negative, so that means everywhere out here you have decreasing slope, but to the right is approaching a slope of 0. Doesn't cross the horizontal asymptote, but yeah, this is sloppy. Okay. Let's pick something south of 0, okay, as in negative a over b. That would be fine. So we'll do dp dt is equal to negative a over b times a minus a negative a over b. Okay? What's that? Oh yeah, I left out the b, sorry. Keep leaving out the b. Okay. And now the this is negative a over b, which is a negative number, times 2a, which is a positive number. This is also negative, so this must be from negative infinity. T is equal to negative infinity, must be approaching that horizontal slope, and everywhere else going downhill. And they don't have to be these curves, but they'll be something like this. So you can tell something graphically about this. These, by the way, are your critical points, here and here. They define this in the 3 regions, above that, between this, and below that. If you had 7 critical points, it would be 6 regions in between, 1 above and 1 below. Okay, so always going to be 1 more than the number of critical points you have. So that's what we did with example 4. Okay? Let's move on to example 5. We'll actually do one with numbers. So let's see. Yeah. This one, I don't think, if I'm... Let's see. Oh, I can erase all inks on that slide. Okay.
Yeah, because this is
Yeah.
not a screen.
Right. So now we go to example 5. And I think we'll start with the graph thing. So, all right, the autonomous equation dy dx is equal to y minus 1 squared. What makes that an autonomous equation?
There's no x's.
There's no x dependence of your derivative.
So no matter what
The
it
function
is,
has x dependence, but the derivative doesn't have x dependence.
no matter what it is, whatever it has respect to, it's not on the other side of the equation.
Right, exactly.
Because
That's it.
dy dt, there would be t.
Yeah. Now, if you wrote y of x, yeah, it has x dependence, but the derivative only depends on y. Okay, absolutely right. Okay, and that's what it is this time. Do you happen to have a guess of where your critical point is?
Okay, so it's where your derivative is 0, right?
Right.
And that's where the derivative is 0. Or let's see, you gotta square that first amount.
Okay. You set the derivative equal to 0. Okay. Now, to solve for y, what I would do first is square root of both sides, and that would give me,
You're lazy, aren't you?
yes.
Equals 0.
Okay, and then
equals 1.
y is equal to 1. There is our one and only critical point. And let's choose that to be right here. Okay, we'll have this being 1, this being 2, blah, blah, blah. This will be a negative 1, and this will be a negative 2. Okay, so here is our horizontal asymptote. Just because at that point, y equal 1, your derivative's got to be 0. Okay, so the functions, anytime it gets close to that, it's got to be approaching 0. Okay. Now, let's pick a point somewhere north of there.
2.
y is equal to 2. What is the derivative there? Yeah, it's 1. Okay? So that means at 2, your slope is going to be 1. Okay? And since it's 1 there, it's going to be approaching 0 here, 1 there, and then probably going on up like that forever. Now that looks to me to be a lot like an exponential function. Okay? Just has that characteristic. All right, let's pick a y something less than.
-1.
Even easier. 0. Okay? And at 0, what's the slope? 1. Okay? And since you said -1, when y is -1, what's the slope?
4.
Right. Okay? So that's going to be very steep. So it's going to be doing something like that. Okay?
So you got a hyperbola.
Yeah. Yeah, hyperbola. Well, no. Well, yeah, it is. Yeah. It probably is hyperbola.
Or at least close.
Yeah.
Not 100%. But
Yeah. And so that first one may not have been an exponential function. It just looks sort of like one. But this one looks a little like a log function. Well, a log function isn't bounded, so probably not. Probably closer to being hyperbola. The problem is, I'm not sure. Well, we just don't know enough about it. We just know this is a positive slope here and a positive slope there, so this is increasing always, that's increasing always. So you're approaching the horizontal asymptote at positive infinity here, approaching at negative infinity here. It's like always increasing. Okay. Now, and I haven't drawn my, good, Victor's here. I'll put you in 237 again. I really shouldn't have put that on top, but when I'm doing my entering attendance, it's more convenient to have them in order, but when in class, I've got to remember them backwards, so, okay. Since Victor is not in both classes, I thought, whoa, that's the wrong class. So, got you later. Yeah. But if you ever don't show up, I got to change the P to an A. Okay. Now, you're right, it's going to be hyperbola, but I just kind of threw those in. These aren't necessarily where these functions go. That's just the direction they're taking. We're example 5 on page 41. Oh, you don't have a book yet. Okay. Now, what they did is say, behold, here's a solution. Okay. Let me, I did this before and I'm going to do it again. This is differential. They ought to be telling you how to get these solutions. So here's how you do it. Again, you rewrite this as dy is equal to y minus 1 squared dx. Right? Why does it do that? Okay. I don't know. I mean, I thought it was because I was near the edge of the page before. This is in the middle of the page and it's doing it. It's just really strange. Okay. Huh? Okay. Now what we're going to do, this is called separation of variables because you can do it. Divide both sides of the equation by y minus 1 squared. Okay. These go out, and that leaves you with, now you integrate both sides, okay, and I can do the right-hand side, I'll do it, x, okay, all right, sorry, that's my side, okay. Now, what's the left-hand side? How are we going to do that? Anyone got a guess?
That looks like a log, or it would be a log, but it's not really.
Not quite.
Trig function,
Not quite. Okay, we're seeing what we could do to solve this integral.
Substitutions.
That won't work.
It's
Oh wait, actually substitution would work. Yeah, you're right, it would work. So let's do that. I was going to do partial fractions, but you don't need that. Substitution will work fine. And what would that be? Let u equal y minus 1. du is equal to dy. And sorry. Our new thing would then be the integral of du over u squared, which I would have written as integral of u to the minus 2 du, which is okay, with a minus in front, minus u to the minus 1. Okay. Okay. Now, the question is, where do you put the c? Okay, you need a c somewhere. Where do you want to put it? And what they do, I'll say again? These are indefinite integrals right now. This one didn't give us anything to go by. So let's put it here with the x, because that's usually the one we put the plus c with. Okay? So this is now, setting those equal to each other, minus, but u is, or you are, y minus 1, so that would be 1 over y minus 1 is equal it's stupid thing. Okay, I did a back arrow. Okay, I had to do it twice for some reason. Equal to x plus c. All right. Now, we want to solve for y. Y is a function of x. So, I guess one thing I would do is multiply both sides of the equation by minus 1. Now, I'm not going to do my c because it can be plus or minus, so we'll just do that. Okay? Or maybe I should. I don't know. Jury's still out on that. Okay? Now what I'm going to do is invert both sides, reciprocate both sides. Y minus 1 is equal to minus 1 over x plus c. Right? Okay? And then I'm going to add 1 to both sides. So y is equal to 1 minus 1 over x plus c. Okay. And that's where they get y of x is equal to 1 minus 1 over x plus c. You see that? Beginning of the second paragraph in example 5. It's aggravating to me that they say, now this is the one parameter value family of solutions for this differential equation. Okay, they say, yeah, see problem 4 in exercise set 2.2. If you're going to do that, why don't you give us that first? Not now. Okay, never mind. I just don't like a few organizational things about this book, but I just gripe a lot. Okay, let's plug in some values for c. What would be an easy value to c to do? 0. I like that. So when c is equal to 0, you'd have y is equal to 1 minus 1 over x. All right, I go 2 back now to do it. So how does that look? Certainly, where is your vertical asymptote then? X can't equal 0. So I sort of want to go to red, but yeah, I think I will go to red. I hate to do this. It just takes so much longer. Okay, vertical asymptote of x equals 0. And let's plug some values in when x is equal to 1. You have 1 minus 1 is 0. Whoops, I need back to black here. I love this thing. Okay. All right. No! I went there and nothing happened. Okay. All right. And when x is, say, 2, that would be 1 minus 1 half, which would be 1 half, which would be right there. Okay? And when x is equal to 3, 1 minus 1/3 would be 2/3. Wait. I'm on the wrong scale. I forgot I put my 1 here and my 2 there. So let's erase those. I don't have to be on a 1-to-1 scale, but I think I want to be. Let's erase that too. All right. Now, 1 was 0 and 2 was 1 half. And 3 was 2/3, I believe it was, wasn't it? So somewhere out there. And let's put in a 1 half, x equal 1 half, and you would have, well, let's do 1/3. X equal 1/3, it would be 1 minus 3 would be a negative 2, so that would be down here, and 2/3 would be 1 minus 3 over 2, that'd be a negative 1 minus 1.5, negative 1/2. So that would be right there. So basically, this would be the curve here. Or, if we did negative values, x equal to a negative 1, be 1 minus 1, that would be a 2. So x equal minus 1, that would be a 2 up here. And then you do the same type of thing. X equal negative 1/3, that would be 1 minus 3 would be 1 minus a minus 3 would be a 4, and that's off scale. So that's going up, and this is going down like this. So there would be when c is equal to 0. And they didn't do that one. They chose x plus 1/2. What a nice, clean little thing to do. I like their other one, have c equal 1. And anything you choose your c to be, then that moves the...
It just moves it around.
Yeah, it moves. You see, you have a vertical asymptote here, a horizontal asymptote, and it just moves the location of the vertical asymptote. Okay? If c were, pick a number other than 0, 1, then you have x plus 1, so your vertical asymptote would be at minus 1. Then it would have been here. So then your curve moves here and there, you know. So it just shifts.
There's no real wrong answer as far as which C you pick.
The problem would give it to you. If
Okay,
you
so
were given an
C
initial,
equals
yeah, if you had an initial value, boundary value, any kind of point that you know is on the curve, that's going to fix. Your curve's going to look like this, but you shift it until you find, like if that point right there is on the curve, then you know you got to shift this down to here, that's over to there, that will be your curve. That's what makes it a family of curves. You use the one that makes sense. Now, attractors and repellers. Sounds like what you use for mosquitoes, doesn't it? You know. suppose that y of x is a non-constant solution of an autonomous differential equation given in 1. This is way back on page 36. Okay? And that C is a critical point of the differential equation. There are basically three types of behavior that Y can exhibit near C. Okay? In 2.9.1, oh, okay. Let me clear this. I don't know if, okay. All right. Now remember, it doesn't have to be the y-axis. Whatever your axis is, wherever it is. We'll just use the y-axis. So here's the critical point C, and they happen to do this in baby blue, so I'll do that too. I don't know why they like that, but they do. But they put the critical points in baby blue. So let's put it right here. Your critical point here is your C. Okay. Now, there could be several of them, but this is just one of them. Okay. Now, the Y's they're going to put in red. Yuck! Okay. We'll do this in red. And let's just say your y0, it's got two places it could be. It could be here or it could be there. Okay? Either place. Okay? Now, what else is going on? What else is going on is what direction is it heading? Okay? We'll put that in black because they did. Okay? If here, okay, you know, I'm going to go on and do the, here your horizontal asymptote is 0. That's because it's a critical point. Your dy dx is 0. Okay, your critical point. That's what makes it critical. Okay, so one option would be with the y up here, it could be an increasing function, or it could be a decreasing function. Okay, one or the other. With the y down here, it could be increasing, or it could be decreasing. But it's got to be, because it's autonomous, it's got to be monotonic. Okay.
Not monotonous.
Yeah. Monotonic. So it's going to either be increasing or decreasing wherever your y is. So that's why you have the four choices. Now, what do they mean by attractors or repellers? I assume they mean by increasing function. This is going away from your critical point. That would be a repeller. That would be an attractor. Down here, your positive slope would be an attractor. Your negative slope would be a repeller. So it just sort of flops over. That doesn't sound very critical to me, okay? But they make a little point about it. So we'll do it. Now, they do come up with something else. A critical point is said to be asymptotically stable, okay? And using a physical analogy, a solution that starts near C, like a charged particle, that over time is drawn to the particle, is an attractor. Then, if over time is pushed away, is a detractor. It's a repeller, okay? In the case the critical point is said to be unstable, then the critical point, an unstable critical point is also called a repeller. Okay. Frankly, this looks great, but for the life of me, I want to say, what's the point? You know, what are they getting at?
Just a way to describe how the curve is acting on the graph.
Yeah, that's what to me it seems like. But
So if you had to like write out an answer as to what happened, I guess.
Yeah. So okay. All right. Here's the deal. And this is what they were doing. You have your 2 points there, the Y's. These are the reds are the Y's, and then you have the arrows. The arrows could be up, they could be down. Okay. Now, when both arrowheads on either side of the dot labeled C point towards C. So this case, where this one's pointing down and that one's pointing up, they're both pointing to C, that's called your stable asymptote. Okay? Asymptotically stable. And in that case, C is an attractor. When both arrowheads on either side of the dot point away from C, that and this, okay, that's called unstable. The critical point is said to be unstable, and an unstable critical point is also called a repeller. So if they're both going toward, it's attractor, and both going away. Okay. Now, okay, so I got it now. But since C exhibits characteristics of both an attractor and a repeller, that would be the case where this one's going away, but this one's going toward, then it would be called a semi-stable critical point. Okay? Or when this was going away and that was going toward, semi-stable critical point. So they show a couple of these in the text. And this one here, in my view, is stable, unstable, and repeller. Okay. Down here you have 2 critical points. This critical point is stable and an attractor, and this one down here is stable, but it is
It's unstable.
yeah. This one's going up, and this one's going down. That's unstable and it's repeller. They just don't show an example of one that's semi-stable. Okay. So homework exercise, that finishes 2-1. Try to do, now let me make sure I always, okay. I think the early class, I remember asking this, do you all have the lavender pages in the back? The answers to odd number of problems in the back of your book? Do they have this little lavender edge to them? Okay, good. And those have odds, right? Right. Okay. So your homework exercises then do either 1 or 3, or both if you choose. Any of the odds 5 through 11, as many or as few as you like. I would do 13, do 15, and then you could think through uh, 17, a null cline. And again, this book is like the linear algebra book. They introduce verbiage in your nomenclature in your problems, okay? So they define what an isocline is in 15 and what a null cline is in 17. And you can work that problem if you choose. Then I would say do 19, any of the odds 21 to 27, do 29, and then think through any of the odds 31 through 30. See, I don't know if, do they have those in the back? That's what I don't know. This is 2.1. See if they have those. I don't think they do. So the discussion things are just completely up to you. 2, 1. I take that back. 2, 1. They don't have answers for anything but starting with 21. So you can do any of those first ones that you want to. Their answers aren't in the back. But please do any of the odds 21 through 27.
Okay, they have the answers for 21, 23, 25, 27, 39, and 41.
Okay, that's what I said, 21 through 27. And then
39, 41. That's it.
either 39 or 41. That's it.
That's kind of sad.
It really is. So don't sweat yourself with the others. So why do we spend so much time doing it? All right, let's move on to 2-2, which to me is where this should have begun. Okay, this other stuff was sort of, it visually probably was satisfactory, but this is where, to me, differential equation begins. It's kind of, okay. The other part's important. And I've already been doing this for you. So, 2.2 is talking about separable equations. And I think I used that term itself. And how we solve these is solution by integration. Okay? I think I'll get off the graph here. Yeah, into the... Consider the first order differential equation dy dx is equal to f of xy. Okay, that's way back. When f does not depend on the y variable, that is f of xy is just g of x, then the new differential equation is dy dx is equal to g of x. Okay? Now, pretty obviously here, if you write that in differential form, that becomes dy is equal to g of x dx, and now integrate both sides. Okay? This gives you y, and this gives you whatever the antiderivative of g is, plus c. Let's call it g of x plus c. If you can do the integration, you solve the differential equation. Your c then becomes whatever your the parameter that determines the family of equations. Okay? So here's the definition. Now this is that's the simplest one. Okay? Let's just do it this example. What is your dy dx is equal to 1 plus e to the 2x. Notice there's no y over there, just x's. So how would you do that? Yep. 1 plus e to the 2x dx. Integrate both sides. Y is equal to?
You got the easy side again.
What's that?
I said you got the easy side again.
Yes, I did that. Okay. I didn't want y'all to struggle with that one. Okay. What does this give you? X
plus
e to the 2x over 2. Antiderivative. Do in reverse. And then plus c. Okay? But in case of doubt, differentiate. Derivative of x is 1. Derivative of e to the 2x is e to the 2x times 2. So you need that 1/2 under there. Yeah. All right. Now, I don't think they gave us any, that's just y is equal to x plus 1/2 e to the 2x plus c. All right. Now, we're going to expand that one more step. Okay? Why they didn't do this to begin with, I don't know, but they didn't. We'll do it. What if not just that it's a g of x, but it's a g of x times h of y? In other words, what if your differential equation is a separable function, that you can separate the x dependence from the y dependence in the multiplication sense? Not addition or subtraction, but multiplication.
Once you separated them out, would you move the y back to the left side?
You put all the y's on one side and all the x's on the other side. In this case, that would be dy over h of y and g of x dx, okay? And then you have to integrate both of those. You wouldn't have a simple y now. You'd have whatever the integral of y would be, depending on whatever the h of y was. Again, they've got to be integrable. So a first order differential equation of this form is said to be separable or have separable variables. So let's do one of those. Dy dx is equal to y squared x e to the 3x plus 4y. Ooh, I thought you said it had to be separable. I can separate the y squared, I can separate the x. Can I separate e to the 3x with 4y?
You would have to take the log of it.
Not quite. Okay? Hint, rule of exponents.
Oh, it'd be e 3x plus e to the 4y.
No, times e to the 4y. Okay? Rewrite this as y squared x e to the 3x times e to the 4y. Because remember the rule for exponents? If you're multiplying same exponent, different bases, keep the base, same bases, different exponents, keep the base, add the exponents. So sure enough, we can separate these two. And what would that be? Dy over, I'm doing two steps at once, y squared e to the 4y equal x e to the 3x dx. And now integrate. All right. It is really ugly, okay? It didn't say it was going to be a rose garden, but it said you could separate them, okay? Now, yeah. This almost looks like table stuff to me. And guess what they say? But in the second equation, yeah. I'm sorry. They wrote two equations down there. I've only written the first one. Okay, in the first equation, yeah, you do that, but they don't give you how to do it. Clever of them, huh? All right. So that one is separable. We're going to leave that alone right now. Okay?
Separate.
Right. Okay? In the other one, that's this one, dy dx is equal to y plus sine of x. Is that separable? Not with a plus or minus. You can divide anything multiplied.
Oh, because it'd be dy minus y?
Yeah, you can't. Well, you mean you're going to subtract the y from both sides.
And multiply by dx.
Okay. I think you got to multiply by dx first, and then you can't get them separated. You have the y dx. Yeah. You can't separate them. That one's not separable. That one is. It's a pain in the neck, but you can separate them. Okay? Now, we can do this one. That's a no sweater, I think, right?
This way.
Yeah.
Would that be x squared over 2? Or is that one of those chain rule type rules?
Kind of like
it's,
that.
it's all
Integration by parts. This is let u be x and du be e to the 3x dx, and then integrate by parts. I mean, yeah, by parts. Okay. This one, I think you can still do that. Well, I'm not sure. I would rewrite this for sure as the integral of y to the minus 2 e to the minus 4y dy. Okay. Now, see, if you differentiate this, it gets worse. If you integrate that, it gets a little better.
Does that mean what?
But you have to do it twice.
Y to the -1, but then you got to worry about even.
Yeah, and then you would have that. So that would take some work to do. This integration by parts works pretty directly on this. Integration by parts on that might work, but it's a little bit more of a pain. Because you see, you can integrate or differentiate this and it doesn't get much worse. But this one is a little better the first time, but I'm not sure you're through with it by then. Oh yeah, once you, you'd have to do it at least twice, but then I'm still not sure you're through. They're not doing it. They're just leave it there. That one's separable, the second one is not. That's all they're saying. Now, observe that by dividing the function h of y, we can write a separable equation. Yeah. Okay, we've done that. Why are they throwing in a p of y here? Yeah, 1 over h of y is p of y. Okay. I don't see that makes it any better, but it is. Okay. From the last form, we can see immediately that number 2 reduces to number 1. When h of y is equal to 1. Yay, okay. Of course, but why would... Okay. Now, if y is equal to phi of x represents the solution for 2, we must have p of phi of x, phi prime of x equal g of x. All right. It seems like they're really muddying the waters here pretty badly. For the life of me, I do not see why they even introduced a p of y in there. Because at the very bottom, then they said h of y and g of x. Yeah. If you can integrate them, integrate them. So why do they introduce the p or the phi? That did nothing for me at all, okay? Because what we had before was exactly what we got now. You know, it's just, the thing is, they've got to be integrable, okay? Equation 4 indicates a procedure for solving separable equations, one parameter family of solutions. All right, let's see what the note says. There's no need to use two constants in the integration of separable equations because, you know, if you use two, then just combine them together to make one. In general, I think you always put it on the x side. Okay? It seems like that's the case. All right. It seemed like they muddied the waters way too. They still didn't tell you how to do it, but if it's integrable, you do it. Okay? Maybe use a table or numerical integration or something, but it's doable. Okay. So let's do example 1. So I'm going to clear all this out of the way. Let's solve this one. Now they write it in a different form this time. 1 plus x dy minus y dx is equal to 0. What would be your first step? Say again? Oh, okay. Go into a Buddhist state of okay, never mind. All right. What might you do? Yes, let's do that. Y dx to both sides of the equation. Now you have 1 plus x dy is equal to y dx. Now what? Okay, what we're trying to do is separate the variables. Get all the one variable on one side and the others on the other. So no, divide by the other stuff. 1 plus x here, 1 plus x here, and divide by y there, divide by y there. Okay? Okay? And the 1 plus x's go out here, and you have dy over y is equal to the y's go out here, dx over 1 plus x here. And now what? Integrate. Okay? Undo that. Okay?
Undo. Not do.
Yeah. And what was the left-hand side? Natural log of y is equal to? That's exactly it. Natural log of 1 plus x plus c. Now, in this case, rather than doing plus c, I would do plus log of c. Because if c is a constant, log c is a constant. What can c not be in this case? Or negative. Because you can't take the log of that. So now your c has to be a positive number, because log c can now be negative, 0, or positive, so no sweat there, but it just makes the whole thing a little easier to deal with, I think. So what we're going to do first is just leave this alone, log y. Yellow wake up? Okay, good deal. Now, what from our rule of logarithms? No, you can't. That you can't do. It's when you have the sum of two logs, that's the log of their product. That would be the log of c times 1 plus x. You don't buy that?
I buy it.
Okay.
I was going to distribute the c.
Okay. Now, this is where calculators really hurt y'all. I was just going to see if they had in here your tables for logarithms. I don't think they do. I don't see them anyway if they have them. They may be in an appendix. Yeah. Okay, that's in the derivatives of them. Yeah. But not just the rule for logarithm. think they hope you're past those now. Let's just see if there's something here. I don't see anything here at all. But the back is Laplace transforms. Let's see if they have anything. Rules for logarithms. No.
I'm not a lumberjack.
You're not a lumberjack? Is that what you said?
Yeah.
I don't see the rules for logarithm. But here's what, this is what they are. The log of a product is the sum of the logs. The reason I said this is where calculators hurt you is that you never, I'm assuming, never had to work with a slide rule. What a slide rule is doing, basically, a slide rule is set up on a log scale. So what you did to multiply two numbers, you found one number on the fixed scale and then moved the 0 on the movable scale there. If you're multiplying, you added the logarithm of this one to the logarithm of that one. The product of that, the sum of that was the product of the two numbers. Because,
seen a slide rule before.
Yeah.
Never used one.
And there was a song back in the 60s about it, but we won't go there. Okay. Now, since we've done that, we can now exponentiate both sides. We had to get rid of the plus sign there, and that's why I put the plus log C. If you take the e of both sides of this, this gives you y is equal to e to the c 1 plus x. And there's your solution. Without a plus c in it, your c is up there in the solution. Okay? Now,
Since the exponential log went out on the left, why did you go out on the right?
oh, I'm sorry.
I'm sitting there like, what is going on?
Oh! So used to. Sorry about that. I forgot to take that out. Okay. Except, no, wait. Yeah. Okay.
That's what they got.
Yeah, it is correct. Except that they did a couple of other things that I sort of glossed over. I was just trying to figure out if it's okay for me to gloss over. This technically should be absolute value of y. Okay? Because you can't take the log of a negative number, you can't take the log of 0. Okay? But of course, we're assuming y is not 0 anyway. If y were 0, this would not be a very interesting problem. It would just be 1 plus x dy is equal to 0. Okay? So we're assuming y is not 0. Now, can we assume it's not negative? Maybe not so easily. But see, you got the same thing here. Then c times this thing can't be negative. So in other words, if you guarantee c is always positive, which you said it had to be to do that in the first place, then x would have to be greater than negative 1. Right? So it can't be 0 and it can't be negative. So x has to be greater than negative 1. Okay? So technically you ought to put that in absolute values too. But then you wind up just taking the values and make everything positive. So I don't know how they weaseled the way out of it. Well, yeah, I do.
Because they switched their plus or minus e, which kind of took care of that.
Right.
With c, since c can be, it's just a constant.
Yeah.
So it's e.
So, I mean, theirs is no clearer than what I said. Just use those, you know. Okay. I mean, they wound up with them being short answer, just do it, okay? And if you have to restrict and say x has to be greater than -1, put that restriction in there. They don't, but it certainly can't be equal to -1. Okay. All right, alternative solution, because each integral results in a logarithm, a judicious choice for the constant, this is what I did, was log c rather than c, and then you have that. I guess what they're saying is if this side is negative, then this side has to be -2, or if this side is positive, that has to be positive, so you're fine. The absolute value bars sort of fall away. It'd be okay for it to be either way, but you just wind up with this.
The words, you know, it may still be advantageous to use natural log C. However, no firm rule can be given. I have a feeling we'll see that more than once.
Yeah. Okay.
In this one.
So basically, we just sort of gloss over that and go. All right. So let's do example 2. So let's go down and do our erase the ink. Good deal. All right. Solve this initial value problem. This time they give you one so we can eliminate the C in a bit. Initial value problem of dy dx is equal to -x over y. Okay? As long as y of 4 is equal to -3. See, there's a little point in me that says that's not an initial value problem, that's some boundary value. That's some, at this place it has to be this. To me, initial means 0 or 1, you know, but not 4, you know. But it means at some value, you know it. Okay, so anyway, with that in place, what will you do first? We write it in differential form, don't we? Okay, no. Okay, dy is equal to minus x over y dx, and then multiply both sides of that by y, okay, and then you have y dy is equal to minus x dx, okay, and then we integrate both sides, and what do we have?
Y squared over 2
Yeah.
equals the negative x squared over 2.
Plus c. All right. Now, seems like a good thing to do to me. Maybe write that constant as c over 2. And then you could say y squared is equal to c plus x, or minus x squared. I hate making mistakes on this thing. It takes so long to clear them. Okay. Okay. Yeah. Whatever. Okay. So there is a solution, but what we want to do is when x is equal to 4, y is equal to -3, so you'd have y, or let's make it 9.
We are out of time.
Oh, we are? So, shucks. It's pretty easy to, I think.
What is left?
Let's just do. It's so long to do. Okay. Y of 4 is equal to -3. So this would be 9 is equal to c minus 16. So c is equal to 25. So your final answer is y squared is equal to 25 minus x squared. Okay. Is that what they got? I was doing it really fast.
Sounds reasonable.
Yes. Or x squared plus y squared is equal to 25. That's going to be a circle. You can either do the top half or the bottom half, but you got to do one or the other. So we'll pick up next time with example 3. Okay?
Example 3?
Huh?
You said example 3?
Yeah, example 3 in 2.2. Homework exercises you can do here would be any of your odds 1 through 21. And any of the odds 23 through 27. And we'll stop there. And if some of those last ones give you problems, you can stop a little earlier. Okay. Have a good weekend.